Welcome back. In the last lecture, we have seen the different formula which we do enter for determining the stability ratio of high impedance differential protection of busbars. In this video lecture, we will try to solve some problems on determining the stability ratio. So before going for the problem, let us see at the general data which will be provided for us, which will help us in solving the problem. See, this is the data which is generally provided. See, it says that a 132 kV bus bar, this is the operating voltage, consists of 2 incoming lines and 4 outgoing lines, which means total number of feeders are 6. So small n is equal to 6. The system is solidly earthed, and the switchgear capacity, this is the switchgear capacity, what we call it as S, capital S, 3500 MVA, and this is the operating voltage which we have already given. So based upon this, the parameters which have been given for us are: number 1, the maximum full load current in one line, which is nothing but the maximum of all the feeder currents. Right. This is 500 amperes. Where it will help us, transformation CT ratio, right? CT ratio, which we call it as N, capital N, is equal to the maximum of all feeder currents. 500 is to 1, which is nothing but it is 500 by 1, it is 500. So N is equal to 500 in this case. The second thing is CT secondary resistance, it is 0.7 ohms, and the lead wire, it is having a resistance of 2 ohms, which means that from the CT, the resistance to your, this is, here it is having 0.7 and here it is 2, total secondary is 2.0 plus 0.7. This is the secondary side impedance. It is 2.7 ohms. This is ZS. And relay load, 1 ampere relay is used, which indicates that it is the pickup value, or I call it as PA. 1 ampere is a pickup value. And the relay load, this is resistance of the load, resistance of overcurrent relay. It is 1 ohm. And they are saying that CT magnetizing current up to 120 volts. See, which means that it is I0, 0.28 milliamperes per volt, and it remains linear up to 120 volts. Beyond 120 volts, it will be constant. So up to 120 volts, let us suppose if I want this current up for 60 volts, 0.28 milliamperes into 60. For 100 means 0.28 milliamperes into 100. For 120 means 0.28 milliamperes into 120. For 130 means after 120 it is saturated, so I have to do only for 120. And after that it is constant. Like this is the significance of CT magnetizing current. So this is the data. This gives us capital N, this gives us, these two will give us ZS, this will give us pickup value and also Z relay, and this will give us I0. Right. So based upon this, we will be determining the different components which will be asked for us. See how many things can be asked, that we will see. See, if you carefully see, there are so many things which are being asked for us. The overcurrent relay in the spill path is set at 1.0 amperes, which means that this is the pickup value, and the voltage setting is 100 volts. This is the voltage setting, V set. High PU you do have, and V set is also there. What you are supposed to determine? Number 1, maximum through fault current up to which the scheme will remain stable. He is asking I external maximum. This is the fault current for which the system will remain stable. Whether the answer in part A is commensurate with the switchgear capacity. Whether the current which you are calculating for this setting voltage and for this pickup current, whether it can hold the system or not, or whether the system can hold this current or not. Sometimes your rating may be less when compared to the actual calculated current. So in that case, you need to adjust your, see, here what you will calculate is I rated current. You are saying that this is the maximum fault current which you can withstand. But if it is greater than your rated current, what will happen? Your system will burn out. So that's why if this value, if it is less than this one, if I rated is less than I maximum fault external fault current, then your I maximum external fault current will be fixed up at I rated. This will become the new value of external maximum fault current. Understood? And the second thing, what they are asking is regarding the minimum internal fault current, which will be detected. If they are not satisfied, what they are asking us to adjust to this value, the setting for detecting minimum internal fault current. This is with regard to I minimum internal fault current. And finally, when you know these two, you can calculate stabilizing resistance and stability ratio. And see, it seems they are asking one more question here. It is required that a break in the pilot wire from a CT carrying a current of 25 amperes and more should be detected by the supervisory relay. So they are asking calculating the setting of supervisory relay also, which means that they are asking so many questions here regarding the maximum external fault current, minimum internal fault current, and also stabilizing resistance and supervisory relay setting. Let's calculate one by one each of them. Okay, I think you do remember the formula. Now let's try to apply each of the formula now. First of all, let's go with this external maximum fault currents, the 1 and 2 cases. See, this is the maximum through fault current up to which your system will remain stable. You do already have the formula, which we do have the setting voltage is equal to N into I into Z by N, right? Where Z is your secondary side CT resistance, I is your, so this is your V setting which you are already given, and this is your maximum external fault current which you are supposed to determine into Z secondary by N. Now I am just rewriting the maximum external fault current which you are supposed to determine. It is equal to N into V set by Z secondary. N is already, we have calculated it. It was 500. Into V setting, it was already given for us, right? It was given as 100, and this was N. It was 500 by 1, so it was 500. And ZS, it's a combination of CD secondary resistance and lead wire. 2 plus 0.7, it is 2.7 ohms. So I am employing these two. 500 into this was 100 by this is 2.7. So if I calculate this one, I'll be getting, don't worry, I am having a calci, I'll be calculating them. 500 into 100 by 2.7. I'm getting somewhere around 18,518.7 amperes. So this is my maximum through fault current up to which my system will remain stable. Now let's see whether this particular answer will coincide with the switchgear capacity. What is the switchgear capacity? The switchgear capacity is given as 3500 MVA and it is operating at 132 kV. If this is the case, what is I rating? Let's see, what is I rating? You know, it is SL by root 3 VA. 3500 by root 3 into 132. 3500 MVA, right? 10 to the power of 6 into 10 to the power of 3. So I'll get 3500 divided by 1.732 divided by 132. So it is 15,308.97 amperes. See, in this case, my ratings of pickup value of 1 ampere and V setting of 100 volts are giving me a maximum current of 18,518, but my system says that it can withstand only 15,308. If the system cannot withstand 18,000 and it can withstand only 15,000, what I should do? I should immediately change the V setting. I should immediately change the voltage setting. So what is my new voltage setting? V setting formula, the same. I maximum fault current, maximum external fault current into ZS by N. So what was it? Now this is my new maximum fault current, because beyond which my system may not be able to withstand, into ZS is 2.7, we have already calculated, by 500. Now let's see what the value which I am getting. So it is somewhere around 82.66 volts, which means that my V setting, initial setting of 100 will not be able to withstand. So I must go with 82.66 volts, right? So in that case, my new value of reset is 82.66, whereas my pickup value is 1 ampere. Now you need to determine the minimum. Now see, I have completed this 1 and 2 regarding the external fault current. Now we are moving on to internal fault current. The minimum internal fault current which you are supposed to detect. What is the minimum internal fault current which you are supposed to detect? We have the formula for that one. V set is equal to, right? So I minimum internal fault current is equal to capital N into I pickup plus small n into I naught. Right. This is 500. This is pickup value is 1. Total number of feeders is 6. I naught. I naught, we do have it. I naught is given up to 0.28 milliamperes per volt. Right. 0.28 milliamperes per volt. How many volts we do have? What is the V setting which we do have now? 0.28 into 10 to the power of minus 3 into voltage is 82.66. This is your leakage current. This is what you should keep here now. So if I calculate it, I naught, I will be getting somewhere around 0.28 into 82.66. So it is 0.0231. Right, this is my I naught. So if I adjust this one, my minimum internal fault current which can be detected is 569.434 amperes. This is the minimum internal fault current which will be detected by my scheme. Minimum internal fault current. Okay. Now my next question. The setting for detecting minimum internal fault current of 500 amperes. Right. Which means that he needs to again set the voltage and he wants to go for 500 amperes. So in that case, my minimum fault current internal, which was my N into I pickup value plus N into I naught, right? This I think I have already obtained here. It was, yeah, initially I have obtained it as 569.434. But what he wants now? He wants only 500. What I need to adjust? When I am trying to adjust this for minimum internal fault, I will be trying to adjust only pickup value. When I am trying to adjust for maximum external fault current, I will be changing V setting. But here for internal faults, I will be varying my IPU. So that's fine. I will be calculating my new value of IPU, 500. So here this is pickup value setting. So I do need now new pickup value. So here this is I pickup new plus this is 6 into earlier already I do have it is 0.0231. 0.0231. So for this one I will getting it is 0.8614 amperes. This is my new pickup value. Okay. See, my old values of 100 volts and 1 ampere of this was pickup value of current and this was V set. Now they have been adjusted to 82.6 volts and 0.8614 amperes, such that my relay thermal rating is thermal rating is being met, and also my minimum internal fault current to be detected is 500 amperes. And next, I think there is one more question. The value of the stabilizing resistance. You know the value of stabilizing resistance, R stabilized plus R relay must be equal to here V set by I pickup value. You have got this one. This is 82.6 by 0.8 here, right? That's 0.861. You need R stabilizing plus R overcurrent relay resistance. I think we have got it already. It was 1 ohm, right? So I'll substitute it here. I'll be getting 1. So R stabilizing is equal to 82.65 0.861 minus 1. And this is somewhere around 94.3 ohms. This is my stabilizing resistance. Okay. So I think this is the end of the problem. Oh, one more thing is there. The setting of the supervisory relay. The setting of the supervisory relay, we do already have the formula, the old V supervisory. That was the last formula which we have dealt in the last class. Yeah. I load, which you need to consider by N into R stabilizing plus R OC relay. So for how much current? I see the question here. Yeah, they are asking for 25 amperes of current, right? They are feeling that 25 amperes of current is being lost. So this is 25 by 500 into R stabilizing. I think I have put it as 94.93 by 1. So if I do this one, this is 25 by 500 into 95.93. If I calculate it, it is 25 into 95.73. 500 is 23 point. So it is 4.79 volts. So this is the supervisory relay setting. Okay. So I think this is the end of the problem. So I hope that now you are able to calculate the different settings of your differential protection of busbars. Okay. So we'll solve more problems in the class. Thank you.